Hey, my name is James Boykin, and I want to quickly solve this optimization problem for you because a lot of my students that I work with struggle with it. So if you need to read the problem, go ahead and pause the video and read it, but I'm going to jump right in. So when you read these problems, I have 5 steps that you want to follow. These 5 steps listed on the board, use these and you will be able to complete any optimization problem. They all follow the same rules. And step 1 is to draw a picture and label. Draw a picture and label what is asked of us in the question. So when you read this question, sometimes they can be difficult because they're word problems. This is what this thing is explaining. We have a rectangle here, we have a width of 24, a length of 36, and then we have these cutouts at each corner. And it's important to understand how these cutouts work because when we draw the volume, because that's what they're asking here, we will have a box similar to the one drawn on the right. So after you draw this figure, the 2 things you want to determine next are your restrictive equation or equations, and then your optimization equation. You will always have only one optimization equation. Once you find the optimization equation, that's the piece that you really want because you can take the derivative of it, set it equal to 0, and it's smooth sailing from there. So here our optimization equation is the volume. Well, you may be asking, well, Zach, how do you know? Well, I've been practicing these problems for years, but what I realized is that when you're reading these problems, you want to emphasize the adjectives of the descriptive words here. Maximize, minimize, the greatest, the least, and usually what follows those are going to be what we're optimizing. So it says here we want to maximize the volume. That means that volume is our optimization equation. We have a box. The volume is length times width times height. That's our optimization equation. Now, for our restrictive equations, sometimes you may have more than one, and here we do. Our restrictive equations are restrictions on the length as well as on the width. And as you can see, we have these x's, and as written out here, we have 24 minus 2x and then 36 minus 2x. Those represent our restrictive equations because we know that this box can only be but 36 minus whatever those x values are. And that's what we're solving for. So when we write those out, we get something similar to this. The length, the width, and the height, all in terms of x. We want one variable. So you may or may not know how to do implicit differentiation right now, but it doesn't matter. When we're doing optimizations, we want everything to be in terms of x or in terms of y or in terms of whatever single variable. Typically, it doesn't matter, but it needs to be one variable. So next up, we have step 3. Rewrite it in terms of one variable. Simple enough. Length times width times height. Height here is just x. We do some algebra, and we set this, and we take the derivative. Once we take the derivative, we set it equal to 0, and now this becomes a simple or a standard maximizing problem. Find the critical points. Once you find the critical points, make sure that you have a max or min. That is the basis of this problem now. However, of course, it's not going to be that simple because they want you to do the quadratic formula. We all know that good thing from pre-calculus. B plus or minus the square root of b squared minus 4 times a times c all over 2a. Here we get these 2 answers here below. Now, once we get these 2 answers, is this both our answer? Do we get both 4.7 and 15.3? No, one of them is correct. And the right one is the 4.7. And now you might be asking, well, why isn't 15.3 also equal to x? Well, it can't be. And the reason why is because 15.3 isn't in our domain, in the domain. So when you're doing all optimization problems, it's important to understand the domain of our functions. And as you can see, I gave you a quick little graph here of what this 4x cubed minus 120x squared minus 864x graph would look like in terms of x. The greatest it can be is 12. That's the limiting factor here. So 15 point whatever isn't even in our domain. So 4.7 is the only thing it could be. And as you can see here in our graph, that it is indeed the maximum. So what we would do is to take that 4.7, plug it into our v of x equation to find the maximum volume. As we can see, the maximum volume is at 1,825 cubic inches. And that is how you do an optimization problem. Now, make sure you always continue to carry through your units throughout these problems, and then you should be good to go. So if you want to work with me personally one-on-one, feel free to reach out. I'm always accepting students, but I hope that this is helpful.